Welcome back to the channel. In today's video, we're diving into connection pooling. Let's explore how it works and why it's crucial for optimizing our application's performance. Let's quickly break down when and why you should use connection pooling. High-volume HTTP requests. When your app makes a lot of HTTP requests, like in a microservice calling external APIs, connection pooling helps by reusing existing connections to save time and resources. Improve performance and reduce latency. Connection pooling minimizes connection setup time, making your app faster, like for e-commerce apps where multiple services are called during page loads. Custom timeout management. You can control how long to wait for different services, making sure important services get more time to respond without causing bottlenecks. Service-specific configuration. Some services need more aggressive connection settings, so connection pooling helps by customizing these settings based on performance needs. Handling multiple routes and hosts. For apps that interact with multiple services, pooling makes managing each service's unique connection settings easier. Scaling microservices. In microservices, efficient connection pooling ensures that inter-service communication remains smooth without unnecessary delays. Preventing resource exhaustion. By limiting active connections, pooling avoids resource exhaustion, like running out of sockets or crashing due to too many open connections. Connection pooling is a game changer when you need to optimize performance, handle multiple requests, or scale your application efficiently. It's especially useful for high-traffic apps, microservices, or any app needing custom connection management. Alright, let's jump into the REST client service project in our IDE. To handle connection pooling with RestTemplate, we need to add the Apache HTTP components jar. Let's go ahead and add this to our pom.xml. You'll see everything on the screen as we do it. Let's dive right in. First, open the RestTemplate configuration class. To handle connection pooling, Apache provides the pooling HTTP client connection manager. Now, let's define the pooling connection manager bean, which will return a pooling HTTP client connection manager. Imagine a busy highway with cars constantly coming and going. Now, imagine a brilliant traffic manager who efficiently directs the traffic flow, reducing congestion and ensuring smooth movement. That's exactly what our pooling HTTP client connection manager does for our HTTP requests. It's the secret sauce to a high-performance application. Create an object of pooling HTTP client connection manager. Alright, time to set a cap on the number of connections. We definitely don't want our connection pool to get flooded, right? With the setMaxTotal method, we can set a limit to keep everything in check. Imagine it's like running a busy restaurant. If we have too many tables, chaos breaks out. We need the perfect balance to keep things running smoothly. By setting setDefaultMaxPerRoute, we're essentially creating a traffic management system for our HTTP requests. We're assigning specific capacity limits to each route, preventing any one route from becoming a bottleneck. This is crucial for maintaining optimal performance, especially under heavy load. Imagine this connection pool like a swimming pool. The pool itself has a maximum capacity. That's our max total connections. It's the overall limit on how many swimmers, connections, the pool can hold at once. Now, think of dividing the pool into 5 lanes. Each lane represents a different route in our application. We can set a limit on how many swimmers can occupy each lane at a time. That's setDefaultMaxPerRoute. It's like reserving a specific number of spots for each lane. But here's the important part. The total number of swimmers across all lanes must never exceed the pool's overall capacity. If too many swimmers jump in at once, the pool gets overcrowded, and some swimmers will have to wait. Similarly, if we allow too many connections on each route, our application can slow down or even crash. By setting max total connections to 100 and setDefaultMaxPerRoute to 25, we ensure that even if all 5 routes are fully used, the total number of connections will never exceed 100. This keeps our pool from getting overcrowded and ensures smooth performance throughout. Now, let's set up the connection config. First, we'll create the connection config object. Let's start by setting the connect timeout, which defines the maximum time to establish a connection with the server. Think of it like waiting in line at a coffee shop. If the line is too long, you might decide to leave. Next, we'll set the socket timeout, which specifies how long to wait for data after the connection has been established. It's like waiting for your coffee to be served. You don't want to wait forever after you've already placed your order. Here, you'll also see other methods like set time to live and set validate after an activity. Let's break them down. Set time to live sets the maximum lifetime of a connection, even if it's not being used. Think of it like having an expiration date on your coffee. No matter how good it is, after a certain time, it's no longer fresh and needs to be discarded. Set validate after an activity is like double-checking a seat at a concert after a long break. It ensures the connection is still good to go after it's been idle for a while. You don't want to sit down and realize the seat's been taken, right? Now, let's take this connection config and apply it to our connection manager, but this time, we'll set it as the default for all routes. Imagine you're setting a universal speed limit for every lane on the highway. No matter which route the traffic connections takes, they all follow the same rules. By assigning this connection config to the connection manager globally, we're ensuring that every route behaves consistently and efficiently, no matter what. Now, suppose you want to set a different max per route for a specific route. Let's do that step by step. First, we'll create an HTTP host. Think of this as pinpointing a specific stop on our network's map. It represents the destination for our route. Next, we'll create an HTTP route. This is like setting up a special lane for that destination on our highway. With HTTP route, you get to define the traffic rules for that particular route, like how many cars connections are allowed in that lane at once. Alright, let's now put the set max per route method to use. In this case, we'll apply it to limit the connections for our localhost 8080 route. Imagine that localhost 8080 is a busy intersection in our highway system. We want to make sure that no matter how much traffic there is, we don't overwhelm this intersection by limiting the number of connections that can pass through it at once. By using set max per route, we can put a cap on the connections for this specific route, ensuring smooth traffic flow and preventing any congestion or overload on localhost 8080. Now, if you want to set a specific connection configuration for this host, localhost 8080, we can do that too. Let's copy the connection configuration we've already created and modify it just for this specific host. Think of it like customizing the rules for a particular lane on our highway. While the general rules apply to all routes, we can tweak them for localhost 8080 to suit its unique needs. Now, to fine-tune our connection settings for specific routes, we can use the setConnectionConfig resolver method from pooling HttpClient connection manager. This method allows us to define custom connection settings, like connection timeouts, socket configurations, and more, specifically for each route. Instead of applying the same rules to all routes, this gives us the flexibility to manage connections differently depending on the host or route. So, let's use setConnectionConfig resolver to customize the connection settings for localhost 8080, ensuring it has optimal configurations for its unique needs without affecting other routes. Next, let's define our HTTP client bean. This is where we'll set the pooling HTTP client connection manager to manage the connections. By integrating the connection manager into the HTTP client, we enable connection pooling across our HTTP requests, ensuring efficient use of resources and optimal performance. Now, let's create the HTTP client object using httpclients.custom. This allows us to build a custom HTTP client, where we can add specific configurations like our connection manager. Now, let's set the connection manager we just created into the HTTP client. Since we've already defined the connection manager bean, all we need to do is inject it into the HTTP client configuration. HttpClient provides multiple methods to customize it based on your use case. For example, let's set evict idle connections, which automatically evicts connections that have been idle for a specified time. This ensures that resources aren't wasted on connections that aren't being used. We can also configure evict expired connections, which clears connections that have expired. This helps prevent stale connections from lingering around and ensures the application uses up-to-date resources. Now that we've created our HTTP client bean, let's move on to our REST client bean, which we already set up in the previous video. Comment out the old code inside the REST client bean. RestTemplate Builder provides a method called requestFactory. In this method, we'll pass a Lambda function that returns a new instance of HTTP Components Client HTTP Request Factory. Create an HTTP Components Client HTTP Request Factory object and pass our customized HTTP client to it. This ensures that our REST template will use the optimized HTTP client configuration we just set up. Now everything is set up, let's start the employee service. Our employee service has successfully started. Now, let's test our configuration by running the REST client code and see how everything works together. In the previous video, we already called the employee service methods from the REST client service. Now, let's see how everything works together. Let's run the REST client service. Oops! We're getting an exception. As you can see in the logs, it says the target port must not be negative. Looks like we've made a mistake in our HTTP host configuration. Let's fix it. As you can see, we used the wrong HTTP host constructor. I mistakenly used the schema and hostname connection, but we actually need to use the hostname and port for the correct configuration. Oops. Need to pass the port as an integer, but I accidentally passed it as a string.
Let's fix that. And run again.
We're getting another exception. Let's check the logs and figure out what went wrong this time. As we can see in the logs, it's saying that it can't connect to localhost 8080. Let's double-check the port where I've started the employee service and make sure everything matches up. Oops. I made a mistake. Employee service is running on port 8081, but we're trying to connect to port 8080. Let's quickly fix this by updating the application.properties file to 8080 and restart the service. Our employee service is get started. Now again run REST client service. Wow! This time, our employee service REST API call went through perfectly. And guess what? If we look at the logs, we can see local connection printed out. That's because we've set up a custom configuration using connection config resolver, and it's working just as planned for this specific route. Our special config is now in action, making everything run smoothly. That's a wrap for today. We've mastered connection pooling in REST client to optimize our HTTP requests. Everything is set up perfectly, and now our system is ready to handle high-volume traffic smoothly. But wait, there's more. In the next video, we'll explore how to manage HTTP headers in your REST API requests, another crucial topic you don't want to miss. Make sure to subscribe and hit that notification bell so you stay updated on all the latest videos. We're just getting started.
See you next time.